the result of today, which will be mainly theoretical, mainly of methodological value, can also have practical relevance, and we will discuss that part. Okay. First of all, you should all be able to access the slides, the notes that I write down. Did you check that or not? You have been able. Okay, perfect. So, what is the main idea? So, what I've shown here is the standard dynamic programming metrics that we all know how to build and whatever. I am going to divide these metrics into smaller submatrices. And differently from what we usually do, these submatrices are not disjoint, but they are overlapping by one row or one column. And also the larger matrix is an n by n, and the smaller matrices are instead t by t. The problem I'm focusing on today is the LCS, so the longest common substring. What is the main idea? If the value of t is sufficiently small, the matrices are not too many. I cannot have too many distinct, different t by t matrices. And so the idea is that if here I have twice the same submatrix, the first time I compute that small submatrix, the second time I only have to access the data that have already been computed. So the main idea again is, okay, I'm going to compute only the distinct t by t matrices, submatrices. Now, there are some problems with this approach. The first one, so B. The first one. What are the elements of my problem? What are the elements of this matrix that actually have an impact on the submatrix? That is, okay, I want to compute what is here. In this submatrix. Or put in another way, what I told you at the beginning is, okay, I want to compute only once two occurrences of the same T by T submatrix. Okay. How can I check, how can I test when two submatrices are the same? Same characters?
If you have the same values in the first column and in the first row, and if the corresponding slices in the two strings are equal.
So we know for sure that the entire T by T submatrix are identical if the first row, the first column, and the characters are the same in both cases. Okay? Why? Because if first row and first column are the same, everything else, and that's a property of the recurrence equation that we have, will be exactly the same. I mean, the same characters are considered, the same numbers, and what. What does that mean? It means that if I want to check if two submatrices are the same, I'm not going to have to look at the entire submatrices, but I'm only looking at the upper and left borders and the strings. This means that, so I need to check the substring of S, the substring of T, upper border and left border. How long does this take? I need to look at T characters of S, T characters of T, T values of the matrix, the upper border, T values of the left border. So overall, big O of T time to test if two submatrices are equal. And that is fine. Good. How many? No, let's forget about another thing. I need to copy this one. Now, let us consider again the two submatrices. LCS again. What do we know about the values that are, so the length of the longest common substring, that are stored in the overall n by n matrix? Are they always the same? Do they increase? Can they decrease?
They
Yes. LCS means that values cannot decrease if we go from left to right or from up to down. Okay? That's trivial. I mean, that's a property of the LCS. So they might stay the same or they increase. They cannot decrease. How much they can increase? Yes. Let's say the two adjacent cells can differ at most by 1. Okay? So they are the same, or the one on the right is one more than the one on the left, and the same for up and down. Okay? Why do I care about these properties? We might have one case. Okay. Nine, 10, 10. So the two T by T submatrices are essentially the same, but not exactly. Why? Because the border, upper and left rows and columns, have the same values except for an additional constant. So the difference between the corresponding values is always the same. In this case, the submatrix on the right has values that are 10 more than the values on the left. So these two submatrices are not equal to each other, but they're very similar. I hope that you agree that if the characters are the same, if the first column and the first row are what I've represented here, also for the last row and the last column, it holds the same property. That is, value by value, the difference is the same. So what do we want to do with these two submatrices? Do we want to consider them different or the same?
We can consider them the same if, subtracting one from another, I have every time the same difference.
Why do we want to consider the same?
Because if this property holds, I can use this difference to predict the next the value of the matrix.
Okay, so the main idea is that the approach that I have introduced says, okay, I have some repetitions. Each time I have a repeated sum matrix, I do not need to compute it from scratch, but I just read the results. So the more cases I'm able to state they are the same, the smaller time I'm going to need to compute them. So I like to have repetitions because in that case I'm able to simply read a result that is being already computed somewhere. So I would like to be able to consider these two submatrices the same. Can I do that? And how can I do that?
You normalize the greater one used to the differences, and every time you have to take a value from the second, you have to.
You have said the correct word. I need to normalize, or I need to reduce in a canonical form. That is, I take this matrix, I take the matrix the first time, and I subtract to all the values what is in the upper left corner. So this one becomes 0, 0, 1, 1, 2, 0, 0. And at this point, if I make this canonicalization of both submatrices, they actually become the same. When I say that the submatrices are actually the same, I'm not only referring to the values, to the numbers, but also to the arrows that we usually have in the dynamic programming matrix. So that's perfect. How many? Now the point is, how many submatrices T by T can I have? Worst case. How many distinct T by T matrix can I have? So, how many distinct T by T matrices can we have? If, because we need one more element, if the input strings are on an alphabet with, let's say, P. Characters. So we are focusing on what is called the fixed size alphabet. And we say we're going to have this alphabet has P characters. How many T by T matrices can I have?
You have two dimension strings, so P derivative to T.
So we need P to T because T long substring of S, okay, of S1 because I write this, no? T long substring of the second string, so that's P possible character, and so P added to T, and
Then you have to match.
how many possible first row, how many possible first column can I have?
Maximum every value can go from 0 to T. So.
So how many? Even upper bound is fine. A non-trivial upper bound, but yes, even trivial.
T derivative to T.
Something like that. Okay. The point is the values in the first row go from 0 to T minus 1 because it's okay. It's too much. We need to do something smarter.
The value increases, so the first value can
So
be T.
yes.
So, it's,
So elaborate on that.
T minus 1, T minus 2. It's,
So if I go from left to right, the value cannot decrease. What can happen if I go from left to right? One position.
they increase every time.
If I increase every time, then never increase. That's what you want.
In this case, they don't increase every time. You see?
No, yes, not the two options.
The bound.
Yeah,
Okay,
either
so-
they increase every time or they never increase.
Yes, but I need a couple of words. Yes, they increase or they stay the same.
Yes.
But can we say something stronger than that? Yes, we can say something stronger than that, but what?
You can check it, the matrix in a dynamic way, but maybe it's not.
Something strong. Again, stay the same or they increase, but say something stronger.
So let's say, or increase by one.
Yes, that's the point.
Okay.
They stay the same or they increase by 1. That's something that we discussed 15 minutes ago, something like that. So what does that mean? So I can take this submatrix and which was already in some canonical form, but now I can 0 is the same, 1 is increases, 0 because it's the same, 1 increases,
Yes.
0 0 0.
Fair enough.
Okay, how many? Yes, binary. So how many distinct matrices? How many T by T?
Two to the no, because it's three
Two
elements.
T,
Three elements.
yeah.
One shot.
Uh,
And
2P raised to 2T, well, that's fine. Okay? Oh, that's good because P is the size of the alphabet is a constant. So this means that the total number of distinct matrices is a simple exponential of t. It's not t at the t. It's 2 or another constant raised at t. Okay, so if t is sufficiently small, I can compute all distinct submatrices and then access them. So I would like T to be small in order to be fast and efficient. But now we go back to our original case. Okay? So, assume that all T by T submatrices have been pre-computed. Okay? And so I've stored them somewhere. Okay? How long is it going to take now to compute the overall matrix?
No, we just have to pick each one.
Yes.
So OT squared to pick each one.
So the
No, not OT squared.
So each submatrix, so the idea is that I go submatrix by submatrix.
Yeah.
So
It's all.
first is 1, then this, and 3, and 4, and so on. Row by row, but at a macro level this time. Submatrix by submatrix. How many submatrices are there?
N over T.
Hmm?
N over T
N over
on each row, and then N over T again. Yes.
Okay.
It's N squared. And T squared.
So this is n square over t square.
So,
How long? So if I have already pre-computed all T by T submatrices, how long will it take to compute the entire matrix?
that's better with T squared. Because some access is constant.
Beware.
But there is a problem because of the other, because we need to check the equality of the substrings. Yes.
How long does it take to compute, for example, this submatrix? So I've stored that somewhere, but how long does it take to compute which submatrix I have to access, to read and in some way copy there? Not copy, but how long does it take?
But it depends on locking storage, I guess.
How long does it take? What do I have to check in order to understand what is the submatrix that I want to read?
First row, first column to match it,
Okay,
and then substrings.
how long?
So substrings is OT.
Yes.
First row, well, I have to take the first row and make it into a series of 0, 1, so I make OT times OT. Oh,
Yes.
This.
We discussed that
Yeah.
sometime. So overall, this is the number of cells. Oops. This is the number of macro cells, and we go to n squared over t time, because we need big O of t to read the first row, the first column, the substring of the first string, the substring of the second string, and at that point we can say that we have organized all submatrices with a search tree, and that each character I go down by one level, and so in big O of t I can find the correct submatrix that I need. I only need to copy the last row and the last column, so that I know what remains of the border, and I can go on with my further explorations. Okay. So previously, we said that the smaller the t, the faster it is. Now it's the opposite.
So it's a trade.
It's a trade-off. So we need to find, and we need both phases. So if we want to be very very precise in our approach, I should say something like, okay, the running time is the sum of the two parts. I'm going to find the value of t that minimizes the sum, so I compute the first derivative and then go on. Okay, I'm not going to be that precise because it's not going to be useful. The main idea is now it's a single exponential in t, and this means that t cannot be much larger than log n, because if t is larger than log n, then this becomes more than n squared, and okay, I'm not gaining anything. So I'm picking t equal to log base 2p of n over 2. Okay? That's essential. Again, my intuition is that it cannot be larger than log n, so I'm trying with some variance of log n, some constants here and there. For this value of t, big O of n squared t is a big O of n squared over log n. Okay? Yes. And my big O of 2p and 2t, this one becomes big O of n. And that's why I've chosen that value of t, essentially. Because the 2 in the fraction essentially compensates the fact that I'm 2 at the exponent in the logarithm. And so if I sum these two quantities, I obtain n squared over log n over all time. Because I need first pre-compute everything and then to go submatrix by submatrix. That's the theoretical, the methodological advance. So I can pre-compute T by T, or in any case smaller submatrices, and use only upper left border to compute the lower right border, and this way I can compute the entire matrix. Again, you understand that pre-computing all T by T matrices is going to require a lot of space, probably a lot of time. Yes, it's going to be big O of n in this case, but still, what we are hiding behind the big O is large, is very large. And so it is hard to believe that this approach is going to be useful in practice. If our value of t is actually log n, something like log n. Anyway, this idea does not rely on the specific value of t. So, can I use the same idea for a constant t? Let's say 4, 5. Yes, the approach is the same, is correct. We can do that. The point is that our time that is n squared over t is still n squared. Still a big O of n squared. But again, in this case, the constant hidden in the big O is small. Is small. And so, again, it depends on the quality of the implementation, depends on the data, and lots of things. I might have some problems where a small value of t makes this technique useful in practice. And it's, again, pre-compute. I expect really lots of duplicated matrices, and therefore pre-computing is a way of caching in some way. Okay, what has been used is cached somewhere, and I'm going to reuse instead of recomputing the matrix. Another point that we need to discuss is that everything here is on square matrix n by n. Square submatrices t by t, and what I have, at least implicitly, assumed is that I can cover my large matrix with a smaller submatrix. I can cover them exactly. What happens if the original matrix is not a square? What happens if the values of n and t do not match perfectly? Well, none of these is a big issue. I mean, I might have at the very right that some t by t matrix is not fully contained into the larger matrix. Again, no big deal. I mean, some rightmost of bottommost parts of the matrix will be computed from scratch or some other way. That's the same. Okay, but that's only a tiny portion of the overall matrix, and so I expect to have my gains. Essentially, the same holds for the assumption that the submatrices are square. There is no need for that. I can have a T by W, let's say, submatrices. And everything else works. I have to be careful how many macro cells I'm going to have, but that's no big deal. That's no big deal. In practice, again, we can go for very small submatrices, again 4 by 4, 5 by 5, or if I have the space, if it does make sense, T is the size of the word, so 64 usually. Because in this case, I'm able to quickly access the data, and the number of matrices, I expect them to be sufficiently small to be stored anyway. Again, in the literature, there are some approaches that exploit this factor, and it's very, very important to study the specific problem and to see if it works or not, but again, in some cases it can speed up the dynamic programming. Okay, the second approach that I want to discuss is heuristic this time. Is heuristic. So, for the second approach, we cannot guarantee that we are going to be faster. We cannot guarantee that the time complexity is better than the usual n squared case. And for describing this heuristic, I'm going with the SCS problem. You can use that also for the LCS and whatever, but it is easier to describe on a minimization problem. That's the sort of problem. Again, dynamic programming. So, what we have usually done is, when I want to compute the value in a given cell, I need to know the three adjacent left and upper cells, and this is called usually the backward dynamic programming. Another version of the dynamic programming is the forward dynamic programming. Here, when I compute the value of a cell, this propagates its value to the adjacent cells to its right and below. But the value is propagated, so propagate its value to the right and below. But this propagation happens only if it improves the current value of the destination cell. Only if it improves the value of the destination. So this means that this propagation happens only if that propagation actually improves the value that is currently stored in the red cell. What might happen, and what is the good case, what we hope that it is going to happen, is that some cells will never receive a value. Some cells that will never receive a value, and so they are completely discarded from the computation. So the main idea is that some portions of the matrix is not actually visited. When I need another ingredient to make this happen, because what I've described so far, each cell receives a value. But suppose that I have an upper bound on the length of the SCS. So, okay, let's look. The super sequence is at most 120 long. Now I refuse to propagate the value if it does not increase, if it does not improve the value in the red state, or the value it wants to write is not better than my upper bound. So, if the red arrow wants to write 121 in the red cell, I forbid that propagation, because it is not going to be able to give me an optimal solution, because it will never be able to improve over the 120 that in some way I already know it's an upper bound. Again, the property is if I move to the right or below, I can only increase, I cannot decrease. So why do I have to write 121 in the red cell if I already know that there is a super sequence that is 120 long? It does not make sense. It will never lead me to a solution that is better than the one that I already have. And so I might not write in that cell, and so that cell might never be visited, it will never be explored. So this means that I'm not, I hope, again, it's a heuristic, so it's not, there is no hard rule. It's based on assumptions and on hopeful cases. So I hope that a large portion of that matrix is not going to be explored, it's not going to be generated. have you already seen an algorithm like this one? Have you already seen an algorithm like this one?
Min-max. In the sense that you crop...
Focus more on the matrix of the dynamic programming. It is true that a min-max has an upper bound, lower bound, and it discards. It's a way of trimming the search tree. That's fine. And that's correct. But my question is more. Have you already seen an algorithm that is forward dynamic programming, even without the fact that we have an upper bound and we avoid visiting some cells?
I don't remember the name, but it was a cross traversal with a time node where the upper bound and lower bound, and you skip an entire path if the expected value.
Forget about skipping the path. Focus on the forward part. Have you already seen a forward dynamic programming algorithm that is not described as a forward dynamic programming algorithm? The answer is yes. Which one?
Maybe a star for
A star is at the end, is what we are going to describe at the end. But before, what kind of forward dynamic programming algorithm have you already studied? You're that close with a star, but no, forward dynamic programming without trimming the search space is not heuristic, it's exact. Dijkstra, exactly. So yes, the Dijkstra algorithm usually is described as a greedy algorithm, and that is true, but it is also a forward dynamic programming algorithm. And that's the recurrence equation and everything. But you move forward and you're not looking backwards. And why did I decide to start from a minimization version of a problem? Because Dijkstra, if you remember, is able to solve the shortest path. It solves the single source, all destination shortest path. The point is, think about the standard of the forward dynamic programming matrix. I can reframe that with a directed graph where the arrows are exactly the ones that I have represented, and the weight of each arrow is what is the contribution of that arrow. And on this graph, finding the optimal solution corresponds to finding the shortest path from the upper left cell to the lower right cell. So, Put in another way, we can see forward dynamic programming as the construction of a directed graph on which shortest path gives me the optimal solution. Again, shortest path means it's a minimum cost solution. That's why I wanted the SCS. I can do the same for a maximization problem, but I need to play with the weights, and it's a bit more complicated to explain. Again, what does it mean? How can I translate the idea that we are propagating a value only if it improves over the value of the destination cell, and if it better than a given upper bound? Essentially means that my Dijkstra algorithm is never going to traverse some arcs, because if you remember Dijkstra, when at each step I add a new vertex, actually a vertex in the frontier, to the set of visited vertices. Once it has been added to the visited vertex, I don't care about the arcs that are incoming into that newly added vertices and have not been visited yet, have not been traversed. And these are exactly those red arcs there. The red arcs that I've traversed there. Upper bound. So I told you, okay, if I have an upper bound, I can avoid not only traversing some arcs, but also I can avoid visiting some vertices. I mean, the Dijkstra achieves the same effect. So once with my Dijkstra I reach my destination, I reach my lower right cell, the procedure stops. So put it in another way, Dijkstra is described to reach all other vertices of the graph, because it's a single source, all destination. But if I'm restricting its application to the case where I have only a single destination, as soon as I reach that destination, my computation stops. Okay? So Dijkstra is able to avoid visiting some vertices, but in some case, that's a case. It's not a feature that is part of the design of Dijkstra. I'm lucky, my destination, my only destination is reached before some of the other vertices, and therefore I'm able to stop the destination, to stop the computation before. The upper bound instead is by design that it is going to avoid some vertices. So a property, a useful strategy to reduce the running time is, okay, with some very naive approach, I compute a common supersequence that is not necessarily optimal. Naive approach, something trivial, okay? Put them together. So this gives me an upper bound on the length of this longest common supersequence, And I use that upper bound to trim even more the set of vertices that I'm going to visit. Again, heuristic means I cannot give you any guarantee. But I expect that in most of the cases I will be able to avoid exploring the entire search space. And so, first step again, trivial upper bound, I'm going to exploit that. Okay, that's going to be helpful. Let's do more of that. So, go on. I've reached the black cell. So, it's Dijkstra, essentially. Okay? So, I have computed the optimal path from my source to the black cell. I add 3 arcs, at most 3 arcs, and I need, and if it is the first time that I reach these 3 cells, I add them to the frontier, so I will keep what is essentially a queue of the frontier, my nodes. And at each step, that's what Dijkstra does, is, okay, pick the best vertex in the frontier, that's my next node, and traverse its 3 forward arcs and go on. The point is always, what is the best vertex in the frontier? Dijkstra states, okay, the next vertex of the frontier that is visited, it becomes visited, is the one that minimizes its cost, the cost of going from the source to that vertex. The A-star approach, the A-star algorithm, extends the Dijkstra approach by incorporating also an estimate of going from a vertex to the destination. So it's pick the vertex V of the frontier that minimizes this is Z, the distance from S to V, which is optimum because it's computed by Dijkstra, plus the estimate of going from V to Z, which is an estimate. Estimate can be anything, I mean, whatever you want. The point is, the more precise the estimate, the more cells I'm not going to visit. Again, if you think about the minimax, usually I have an heuristic estimate of the value of what I have in my situation. The more precise it is, the smaller the visit search tree becomes. And that's the same idea. So I'm picking the vertex that minimizes that sum. The important property is that if my estimate is smaller than or equal to the true distance, so if my estimate is always smaller than the true distance, then A star always finds an optimal solution.
How can we estimate the less than the two distance? You get it in a wrong way.
No. That's a good observation. How can it be? But we have example. So Dijkstra is a restricted version of the A star algorithm where the estimate is always 0. So that's a trivial estimate, okay? We have a smart, and if you think about, again, shortest path, if you think about a map, geographical application, the shortest way to go from Milan to Oslo, okay? What is a good estimate is the Euclidean distance, straight line. I mean, linear area. Okay, that's smaller than or equal than the actual solution, and that's very easy to compute. And that is what is usually used in practice if you want to compute the shortest way to go from one place to another one. So we have an estimate that is very easy, very fast to compute. It is always smaller than or equal than the true distance, and it will allow me to trim a lot the search space. But we started from the shortest common subsequence. What is and not only that, but the problem that I want to discuss is the SCS on 3 strings. Yes. Okay? So, the dynamic programming matrix is 3-dimensional instead of bidimensional. It doesn't matter. Forward dynamic programming, each cell will try to propagate its value to 7, not 3, adjacent cells. because we have three different axes. But the rule is the same. Okay, it propagates only if it improves on the current value. What is, so the point is, my matrix, so let's say that S1, S2, S3, no, the strings S1, S2, S3, okay? So I'm going to compute MIJK, that is shortest supersequence of the first I characters of S1, the first J characters of S2, and the first K characters of S3. So if I want to apply the A star approach, I need an estimate. I need a lower bound of the SCS of S1 from I plus 1 to the end, S2 J plus 1 to the end, and S3 K plus 1 to the end. Okay? It's an argument of semester. Okay. Why did I move to 3 strings? Because we discussed last lecture, it going from 2 to 3 increases a lot the space needed, the space complexity. The time also goes from n squared to n cube. And so n squared might be more or less acceptable, n cube, it's much worse. And so while I can be feasible to compute the optimal solution on 2 strings with the standard dynamic programming approach, if I want the solution on 3 strings, everything is much more complex and worthy of any smart strategy I can apply to make it faster. So the goal right now is I need a lower bound, and easy to compute, not entirely stupid. Lower bound of the SCS on those 3 strings.
The lower bound can be
I mean, 0 is not good enough. Okay?
for example, the minimum length of the slices.
What?
The minimum length of the slices. The minimum value from the length of S1, of the suffix of S1, the suffix of
One proposal is the minimum of length of S1 minus I, length of S2 minus J, this one? Okay? Can you do something better? Yeah, I mean, okay, that's a lower bound. That's better than 0, for sure.
Maximum. Or
The maximum, right? Yeah, no, that's correct, the maximum. I don't remember if you say minimum or maximum, but yes, that's okay. Something better? What, okay, let's say, to the one limitation of the lower bound you proposed is that essentially each input sequence is considered independently.
The amount of characters that are shared plus the amount of characters that are not.
But if they're
Maybe you can try to launch to compute the SCS on the two combination of what the input, and then you get the word.
yes, and that's why I stressed you the moving from 2 to 3 sequences, and I told you 2 to 3 input strings. I told you, okay, 2 is feasible, 3 is not. So a better lower bound is the maximum of the SCS of S1 I plus 1 S2 J plus 1 J plus 1 S1 I plus 1 S3 K plus 1 so I mean, it's a lower bound. It's better than considering each sequence independently. It's good enough. I mean, we can do better than that for sure, but it's good enough, and it's sufficiently fast to compute in practice.
Yeah.
Why? No, you're not convinced?
No. How is it fast?
Okay, that's the point is, I do not have to recompute all those pairwise shortest common supersequence each time, because I store the SCS, not this, the matrix of the SCS, so the dynamic programming matrix of S1 reverse, S2 reverse. The same is S1 reverse, S2 reverse, and MSCS of S2 reverse, S3 reverse. Let's focus on the first S1 the dynamic programming matrix of the SCS S1 reverse, S2 reverse. I keep the entire matrix, because the ij, the PQ cell there, so here, MPQ, what is? Is the length of the shortest common supersequence of the first P characters of S1 reverse and the first Q characters of S2 reverse, that is the reverse of, but the length is the same over, of the last P characters of S1, the last P characters of S2. So this means that I compute the three shortest common supersequences once. I keep the entire matrices, and then any time that I need to compute a lower bound, I have only to check to read the values in the three dynamic programming matrices. So I'm not computing supersequences after supersequences after supersequences. Three computations and that's all. It's a heuristic. So I have no guarantee that this lower bound is good enough and that the overall three-dimensional matrix is going to be visited only in a small part. We have to run it in practice on the actual data and whatever to see if it works or not. In practice, it works. Usually, it's a good heuristic and it's a good rollout. Again, what the point is, heuristics have practical motivations. Not really. Still, the study of algorithms allow us to provide good lower bound, upper bound, whatever we needed, heuristics that can be useful in practice. So, efficiency and efficient algorithms, which is the title of the course, are always a good idea. And that's all for today.
So,
yes?
we cannot use this approach for two strings. Like this, of course, this lower bound.
I mean, if you go with if you go for two strings, I mean, then your original proposal makes sense.
Okay.
It's something that you can use that, and I would probably actually go for a naive approach, compute a solution, trim down, and then a mixture of more lower bounds.
Okay.
In that case, that's an upper bound, but that's useful in any case. So yes, this one has been developed for three strings. A star works for any optimization problem, minimization or maximization. In case of maximization, you don't need a lower bound, you need an upper bound, everything is reversed. Dijkstra is a special case of a star. There are other heuristic techniques that like to work on shortest path. So the specific lower bound we have described here is for the shortest common supersequence. The A star idea is fully general. And the idea of reframing dynamic programming as a shortest path problem, again, is something that applies to any dynamic programming approach. So there is a lot that you can adapt in a different context. Also, keep in mind that A star essentially states that if the estimate is smaller than or equal than the true distance, then we have an optimal solution. But I can apply that idea even if I have no guarantee that the estimate is smaller than the true distance. In that case, I might lose the optimal solution, okay? But it should be fast enough. in any case. So, again, try to understand the more formal setting, but I think that once you need an heuristic, you have lots of corners that you have to cut to be faster. Again, it depends on your problem. If it's so huge and difficult to manage that any estimate is good, okay, that's a good idea. That's something that might speed up your computation a lot. Again, it depends a lot on the problem. Ok? Ok, abbiamo finito oggi.